discuss the solving systems of linear equations. Okay, that is very important. You see, we have three equations: a1x, a2y, a3z. Add it together equal to b1. These are linear equations with three components. Okay, x, y, and z components. And this is the second equation. This is the third equation. Okay, so there is a way of writing equations. This is called a matrix form. Okay, this black part, a1, a2, a3. These are the coefficients a1, a2, and a3, and these are the variables x, y, and z. You see, we have organized in such a way that all the coefficients of x are in the same column, coefficients of y in the same column, coefficients of the z in the same column, and one row corresponds to all the coefficients of one equation. Okay, so this is called a coefficient matrix because all are in the, so this is a row of a matrix, this is a column of a matrix. So this is a 3 by 3 matrix, okay, for equal number of equations and unknowns. That means if there are three unknowns, x, y, and z, whose values we don't know, we have to have three equations to be able to solve them, okay? So you see this b1, b2, b3 are the intercepts of the equation, and if I remove this one, so this whole matrix together, it's a 4 by 4 matrix, it will be called augmented matrix. You see all the values are known, the coefficients values are known, and the intercepts values are known also. So this will be called an augmented matrix. And just this black part, this the 3 by 3 matrix coefficients will be called a coefficient matrix. So now what we are trying to show, in this equation, what we are trying to show that for this 3, so there will be corresponding x, y, z values, so that at a certain place these three equations will be in the lines. These are just a line, so they will intersect with each other, and those points will be the points where we'll have a corresponding value of x, y, z, solved value. So I want to show you that how come we are being able to represent a linear equation in the form of a matrix. For that, we go back a little bit, again talk one more time the relation between the matrices and the vectors. We have already talked about vectors, so let's see one more time. So let's say A is a vector in a two-dimensional coordinate plane. Okay, so this is like in the x direction it's a 6 and the y direction is 5. Then you can reach the tip of the vector. Okay, so like you go 6 steps in the x and then 5 steps in the vertically, and then you can reach the tip. So as we said, this is the magnitude of the vector, and this is the direction. Okay, vectors are also considered as a list of numbers. How? Because we can represent the tip of a vector as a 6 and 5. 6 for x, 5 for y. Okay, so there is another way of writing this. So vector A is written as a matrix. Okay, this is a matrix. So we are saying in linear algebra, generally we consider vectors to be rooted at the origin. Okay, so origin is this one, where this is the origin, and we always say in linear algebra that vectors are rooted at the origin. Okay, but in a three-dimensional space, vectors can be anywhere. I will probably show you a picture where we'll show that let's say in this room, in a three-dimensional room, there is a line anywhere in the middle. Okay, so it will be in a three-dimensional space. So how we can represent a vector in a three-dimensional space? If in a two-dimensional space we have x and y coordinates, in the three-dimensional space we'll have three coordinates, x, y, and z. Okay, let's say there's another vector A which is written as 0, -3, 5. So 0 is corresponding to the x coordinate, -3 corresponds to the y coordinate, and 5 corresponds to the z coordinate. Okay, so this is a way of just writing the coordinates of the vector A. And this is in a matrix form for a two-dimensional plane. That's why it's a column vector in a two-dimensional. And this is a column vector for a three-dimensional space. Now we'll talk about the linear combinations of vector, which are nothing but giving us the linear equations.